Hi everyone, good morning.
Morning.
Hey, we're going to talk today about making C++ standard parallelism multidimensional. So don't worry, I'm not coming with giant proposals today, so don't be too concerned. And in particular, this is a talk about ideas that I'm still in the kitchen and I'm making the sourdough starter and I'm kneading the dough. So I haven't baked these ideas. You're not heading to the bakery today. And so I'll talk about the support that we have in the standard for parallelism today, not just multidimensional, but generally. So we have parallel algorithms, we have data parallel types, we have permissions to parallelize. And then I'll give some justification for why we should support parallel multidimensional algorithms in C++. Why should we go multidimensional? And then, assuming that we want that, then I'll talk about what supporting multidimensionality and parallelism together might look like. So before I begin, I need to make clear what I mean by parallelism. And I owe it to Daisy Hoemmen, this continuum, this contrast between parallelism and concurrency. And so I opt into parallelism because I want to relax execution order for the sake of performance. And concurrency for me means the opposite of that. It means I want to constrain execution order, and I want to do that for the sake of correctness because my algorithm needs it. And when I say relax order, that can mean if I have two things, they could happen in either order with respect to each other. That's parallelism. Or they could happen in any order with respect to the caller. That's asynchrony. But both of those things are, in my mind, parallelism. And that's really about permission. So with concurrency, sometimes I actually need threads. I need some number of threads that's bigger than one because I'm making some promise about forward progress, and that's kind of a constraint on order in the way things execute. Whereas parallelism is more about the permission to execute, not necessarily actually having multiple threads. And so with concurrency, one would talk about happens before. That's an order constraint. So with parallelism, it's the opposite of that. Standard C++ supports parallelism in 4 different ways today. There's asynchronous execution, there are parallel algorithms, there are data parallel types and operations, and there are arrays. With asynchronous execution, that can mean either explicitly creating threads that run in the background. We could type stood thread or jthread or stood async. Or it could mean creating asynchronous dependent tasks that might execute asynchronously on a scheduler. So that's stood execution or coroutines. Then there are parallel algorithms. And we have a variety of those today. We have, in C++ 17, we were introduced to the iterator-based parallel algorithms. Thanks to Ruslan, we have the parallel ranges algorithms in C++ 26. C++ 26 with stood execution also introduces asynchronous parallel algorithms. So bulk, unchunked, and bulk chunked. It also introduces the linear algebra algorithms, which are parallel. And also there are some proposals for multidimensional algorithms that are in the pipeline right now. So the copy and fill for MD-span, those are parallel algorithms that have finished design review in LEWG and are awaiting wording review in LWG. And then multidimensional for each proposal, that's pending design review, but it's been submitted in the April mailing. And so I've shown on the screen some examples of that. For each index, that's the multidimensional for each that's proposed. The matrix vector product, that's part of the linear algebra library in C++ 26. And then ranges transform, that's part of the parallel ranges that we have in C++ 26. And then there are data parallel types and operations. And maybe you don't necessarily, you think of that as a SIMD thing, but we've had those the whole time because you can do bitwise operations on integers. And those are parallel algorithms. Those are bitwise parallel algorithms on words. And those have been there from the beginning. We got new ones in C++ 20 with the bit header. And then there's actual SIMD. So those are, instead of bitwise operations on words, those are element-wise operations on chunks of words, groups of words together. And there's a bit of a bit of example of SIMD parallel algorithm on the right. You don't have to read the whole thing. But the point is that those come with types and operations. So operations include arithmetic, math, computations on SIMD types, but also ways to get them from memory and put them back. Loads, stores, gathers, scatters. And the parallel algorithms and SIMD together start to build a system for processing data in parallel. The global algorithms are global. Parallel algorithms are global. They process your whole data structure. They work on the outer loop. Whereas data parallel types are local. They work on little chunks of your data. And we'll talk more about this later, this interaction between the global and the local. But it's important to think of that. Like parallel algorithms are the whole thing. You know, the outer loop, the whole data structure. SIMD types are the current little one that I'm working on right now. And then there are arrays. There are different kinds of arrays. There are raw arrays, there are memory allocations, there are ways to express contiguity in the standard, lots of ways to do that. There are containers like vector and array, and views like span and string view and MD span. There are contiguous iterator, contiguous range. There's even val array. You know, people like to say bad things about val array, but people do actually use val array. So I always feel bad when I hear people saying bad things about val array because it makes other people feel bad. So be gentle, okay? Even though I don't really like its design, it's still a thing that people use. MD spans have accessors, and those are ways to express contiguity. And then there are ways to express overalignment, like assume aligned or is sufficiently aligned. And it's a little funny that I've mentioned all these things about arrays, because you don't think of arrays as having things to do with parallelism, but it turns out they have quite a bit to do with parallelism. They're enabling technology for parallelism, and I'll elaborate on that in this talk. And arrays actually reveal three properties that enable parallelism: disjointness, locality, and coupling. And I'll talk about that as we go. So we make a lot of different assumptions about arrays. When you create an array and use an array, you assume that if I have distinct indices, that the corresponding elements are distinct. It's a reasonable assumption. And I'm calling that disjointness for the case of one array. So that different indices, different elements. And for two arrays, we have the promise from the standard that if I create two objects by default, or if I create two allocations, they don't overlap in memory. So here I've created an array X, an array Y, and I know that those arrays don't overlap in memory. And I also know when I create an array that it has a certain kind of locality. So for example, I know that if I have an element and I get the next index, if I add one to the index, that next element is next in memory as well. And that's called spatial locality, or it enables spatial locality. And I also know that if I take an index and an array, I know that that address in memory generally doesn't change. Of course, vectors could be reallocated, but assuming it's the same allocation. And that invariant enables temporal locality, or reuse. And then there's something that I'm calling coupling. Coupling is really about things like alignment and the relationship between memory and local data structures. And so this knowing that arrays are aligned when I allocate them, and being able to allocate over-aligned data, that's something that I'm calling coupling, and I'll elaborate that later in the talk. And maybe if you're paying close attention to the code, you'll notice this. And I'm not just comparing my pointers with less than and equal to, because if I use the built-in arithmetic operators on pointers, that only defines a partial order. If the allocations aren't related, then the comparison values are unspecified. But it turns out that if you use the standard function objects, like less or less equal, then you can compare pointers and there's a total order on them. And so that's how you can decide that pointers are overlapping or not overlapping. So disjointness enables permission to reorder writes. Disjointness is really, in terms of parallelism, is about writing to the array. And so For one array, disjointness is about every element having a unique index, so that different indices refer to different elements. Now that sounds trivial. That's normally true when you allocate an array, different indices, different elements, right? Well, there are different ways of describing arrays. So for example, in the basic linear algebra subroutines, the C and Fortran standard for linear algebra operations, there's something called an, oh, that's not AXB, that's a different routine. Let's see if I can remember it. GenV, sorry. I spelled it wrong. Okay, GenV, that's the Blase's basic matrix vector multiply, thank you. And it computes y equals beta times y, where y is a vector, beta is a scalar, plus alpha times a times x, where alpha is a scalar and a is a matrix. And the Blase takes integer strides for the vector. So the distance between consecutive elements in memory in terms of words. And you're not allowed to put 0 there. But a 0 stride can make mathematical sense. And what that does is if I'm accessing an array in read-only fashion, and the stride is 0, then every index in the array points to the same address in memory, points to the same element. And that's a great way to represent a vector whose elements are all the same. And that makes total mathematical sense. For example, if I went to compute the sums of the rows of the matrix A, a good way to do that is a matrix vector multiply where the vector is all ones. And so rather than storing 1, 1, 1, 1 in memory, I could just have a single 1 there and a stride 0 array. But the Blase doesn't let me do that. But I could imagine doing that. And with something like MDSpan, you can represent that. And also, like popular formats for people who program in Python, who do deep learning or numerical computations in Python, they often support 0 strides for arrays, like DLPack is an example. And so if I can have 0 strides, I don't have disjointness. Disjointness is about, like I had said, it's about permission to reorder writes. And for 2 arrays, it's about asking whether the arrays overlap. Are there indices where like some index from this array and a different index from a different array point to the same element in memory? And if I know disjointness, both kinds of disjointness, that gives me total permission to parallelize writes on the arrays. I can vectorize, which means reordering, optimizing for chunks, for example, for SIMD instructions. And I can parallelize with the parallel algorithm. I'm showing memcopy and memmove here. The difference between them is that memmove permits the arrays to overlap, and memcopy does not. And what that means is memcopy is a parallel algorithm because it gives the user gives the algorithm permission to reorder the writes in any way it pleases. And so memcopy is all right with the disjoint array. So that's, disjointness is useful. Even if you never create threads or care about multiple threads, you still care about parallelism if you call memcopy. So I talked about these 2 questions for disjointness. C++ has some ways to represent this already. There are language rules about arrays when I allocate them. When I have different allocations or create different objects, they don't overlap in memory by default. There is a way to, in theory, you can say that, you can state in C++ that I'm assuming that 2 arrays are disjoint. And you could do that now with the assume declaration. But in practice, the compilers that we've seen aren't really able to make use of this. And the issue is, yeah, I've made this algebraic statement that I have a pointer and another pointer and a length, and I promise that this is less than that and this is less than that. And that's great, that's algebra. How does the compiler know what I meant by that? It doesn't, right? Like, I just said some math, and the compiler would have to figure out pattern match on this somehow and figure out that I meant to say something about overlapping. And that's kind of hard. It would be nice if I could just tell the compiler that. So you may know the restrict keyword. And it's not a C++ standard feature, but a lot of C++ programmers use it because it comes to us from the C standard. And it's a popular language extension in C++ compilers. So the compiler lets you do it, and it has some meaning there to say it. And generally, when users use restrict, they want it to mean something like, I promise that this points to an array, that points to an array, and the arrays don't overlap. It means something a lot more complicated than that about pointer expressions. C++ standard has resisted adopting it, and there's a bit of a history. The alias sets proposal from 2014 by Hal Finkel and others talks a little bit about that history. But if you could use restrict, it turns out that compilers can optimize quite a bit. So for example, on the left, I'm showing a copy backwards algorithm where I have two arrays and a length, and I'm copying from the input array Q to the output array P. And I'm doing it backwards for some reason. And but only if you put restrict there, a few compilers, at least the ones I've tested, will literally turn this into memcopy. You'll look in the code and there'll be a call to memcopy in there. And there are other examples, for the example on the right, I have two arrays that are interleaved with each other. So I have T, I have S. I'm copying every other element from S to T. But my S array they skip every other element, and the S array starts one after the T array. So the T array elements are blue, the S array elements are orange, and they don't overlap. The elements don't overlap. But they do occupy contiguous chunks together. So if I don't have a way to talk about overlap, I can't really declare that those two things don't overlap. And really what I want to do is I want to partition things. I would like to declaratively say, I have an array, I break it into disjoint chunks, and I know that if I write to this chunk, I'm not going to write to that chunk, and vice versa. But generally when I have arrays, like the things that I can do with arrays are slice them and not partition them. The difference is that when I take a slice of an array, I'm viewing a subset of the elements, and my subset view exists at the same time as the original view. And so now I have two views, and their elements overlap. I've created aliasing. But I didn't really want to do that. So the example I'm showing here on the left is quicksort, which I've expressed with span. So I take my input span, I partition it, pick a P in the middle, a pivot, and I say, okay, everything on the left, I take a view of that. Everything on the right, I take a view of that. Now I can call quicksort. I could call it in parallel because I know those things are disjoint. And then I return. I can recurse on that. And so even though I know that x left and x right, the two partitions, don't overlap, they overlap with the parent view. And all those lifetimes exist. They all exist at the same time. And I'd really like to be able to partition, to have a way to say, okay, these subviews of the original parent view are disjoint. And I promise that I'll never get to the parent view while I'm using the children views. You can kind of express that in C++ by creating libraries that encourage this kind of programmer discipline. So you can create, for example, I show an apply left-right function, and what that does is it takes a pivot and some view, it splits it in the middle, and it executes the left side and then the right side. So you're not allowed to see the fact that I created subviews. And then I can express quicksort in that way. And here, that quicksort version, that doesn't let me see the existence of my subviews while my parent view is active. But it's still there. So that's kind of a library discipline. In Rust, you can say things like this, and the borrow checker protects you. So when I when I call split at mute in Rust, I create this partition, x left and x right, and I'm not allowed to write to x while x left and x right are present. Like the language stops me from doing that. And then I can run this in parallel. So it would be nice if I could say that.
Mark?
Yeah?
Can we go back to the previous slide, please?
Yeah.
What is the template for doing there in the apply left, right?
Oh, yeah. So I didn't explain split left, right. This is just kind of hypothetical code. But you can imagine that split left, right creates a view x left and a view x right, and it returns a tuple of the two views. And so because it's a tuple, it has a compile time size, and so therefore I can iterate over the elements of the tuple. And so what I'm doing there is I'm calling the input function for each element of that partition, but I'm calling it in sequence. That could also be, instead of a template for, it could be some sort of parallel construct, but you're allowed to do that. But yeah, thanks for the question. So it would be nice if I could express partitions in C++. It's kind of hard. Another way to express disjointness would be, for example, the alias sets proposal from 2014 that was led by Hal Finkel. It would be nice if we could teach it about standard library things, and so it could know that a span represents a contiguous chunk of memory. But if I had partitioning, I wouldn't really need this. Like, I don't want to use assume if the language just gets me the guarantee for free. But if I have to do assume kinds of things, then I'll do them. And there's a question of how much we really need this. So we'll revisit this topic later. Now I'll go from disjointness to spatial locality. And spatial locality comes from contiguity. So contiguity means if I get the next index in my array, it's the next one in memory. That's really virtual memory, not physical memory. I don't necessarily have control over physical memory, but virtual memory is a kind of hint for physical memory. You would hope that if the next address in virtual memory, I would like it to be the next address in physical memory and to get the corresponding performance benefits. And this is really important for programmers in all sorts of languages. It was in fact important enough for C++ users that one of the original DRs filed against the original C++ 98 was, I would like std vector to promise contiguity in memory. And it didn't do that in C++ 98. So that was fixed as a DR for C++ 03. And computers optimize contiguous access in all sorts of ways. I show an example on the right of the IBM 7030, the stretch, that was first installed in 1961 in Los Alamos. That was an early adopter of something called interleaved memory, which meant that there are different banks of memory. And when you loaded contiguous addresses, you would go from one bank to the next bank to the next bank to the next bank, and then it would loop around. So there were 4 bank chunks of memory. You could have multiple banks to get more capacity. But up to some limit, it was a 4 bank interleaving. And so if you, and the point of that interleaving was to hide memory latency for each bank. So you'd start your access, and while you're waiting for that, you could start the next access and go on. And so that the interleaved memory, that was one way to hide latency and therefore optimize for contiguous access. You might be familiar with how caches work, that there are cache lines, and the point of a cache line is to amortize the latency of contiguous access. So if you know you're doing contiguous access, you pay once for the whole cache line and not once per word. Our GPUs have something called coalesced access, which optimizes for the case of contiguous access when different threads are sharing that chunk. So it's a little bit like cache lines. There's prefetching. There's asynchronous memcopy that our GPU supports. Some other systems support that. Memory pages and the way that the translation look-aside buffer work maybe they don't optimize, but they favor contiguous access. And if you really stride across memory, you'll pay for it. It's hard to find computers that deliberately do not optimize for contiguous access. I can think of maybe the Terra and then later Cray MTA or XMT, which would randomly hash your memory access to avoid hammering one memory module too much. And those architectures optimize for pointer chasing trees and lists and things like that. Those are a little unusual. They do exist, but most architectures are optimized for contiguous access. The stretch is a really fascinating historical bit. So yeah, it was ahead of its time and very ambitious. And even though it didn't succeed in terms of achieving its immediate goals, like in terms of setting what future computers would look like, it was an amazing achievement. And so I talked about spatial locality, optimizing for contiguous access. Temporal locality is optimizing for reuse, so locality in time instead of space. And I like this quote from a paper that talks about what became the Institute of Advanced Studies IAS machine, or later called MANIAC, like a template for the design of post-war computer architectures. And even that paper talks about memory hierarchies, because you can have slow memory that's huge, like your huge memory is slow, your fast memory is small, and you can't get fast and huge. That's not a thing. Even back then, you couldn't get fast and huge. I remember my advisor's advisor talking about out-of-core algorithms before core memory existed, so it's anachronistic to call it out-of-core, where he had a slow memory that was a rotating drum, and a fast memory that was literally, I think it was a selectron, so something that looked a little bit like a cathode ray tube. And it had a monitor where you could see the dots that were the bits in your memory. That was pretty wild. But yeah, the issue with the drum is that, oh, thank you, it would rotate around. And so if you missed it, if you missed your spot, you'd have to wait for this mechanical thing to rotate. And so you're paying that latency. You'd rather not have to pay that latency on every access. And I showed some of the folks who were involved in that IAS machine. This is quite a portrait. I think that's at Princeton in front of that IAS machine. And you might recognize the second guy from the right. He was portrayed in a movie recently. But I like this one because John von Neumann is smiling. And people like to show his Los Alamos badge photo, and he looks really kind of grumpy there. But I would be too, because when you start working at a lab, you have to go do a lot of paperwork and run around, and I imagine he was tired. So he's in his element here, so I'm happy. So memory reuse is about optimizing for the memory hierarchy. And so memory hierarchy matters at all levels of parallelism, and it tends to reward a chunk-wise reuse pattern. So I want to get the most out of my small, fast memory. And so I size my local chunks to fit in my small, fast memory. I load that in, I do as much work with it as I can, and then when I can't do any more with it, I put it back, make room for the next chunk, so that I get the most out of my small and fast memory. And people don't think of vector computers, they think of that in contrast with cache-based computers. People will say that, vector and cache-based. Well, even the Cray 1 had a memory hierarchy and optimized for temporal locality as well as spatial locality. And so, for example, the Cray 1 had a big register file for vector data. And if you cleverly, if the latencies worked out for the instructions, you could do something called chaining. And what that meant was you would load your data from memory, your vector data. You'd bring it into the vector register. And then you could reuse that across multiple arithmetic operations or multiple vector instructions. And that was one of the justifications. Chaining was one of the justifications for having a vector register file and not just loading things from memory, doing the arithmetic on it, and putting back in memory. And so the Cray 1 actually had a memory hierarchy. That was a lesson learned from earlier memory vector machines like the CDC Star 100. And the Cray 1 also had something called immediate register files, like the B, what do they call those? The B and the T register files for scalars and addresses. And those were very, very low latency to transfer from them to the main registers. And they also supported asynchronous block transfers to and from memory. It's kind of wild to see these ideas come again and again. But it just shows like temporal locality is everything. And I've been talking about locality and reuse. There's a bit of foreshadowing here, like why am I talking about this? I haven't said anything about multidimensional yet. Well, it turns out if I'm doing a one-dimensional algorithm and I'm just passing once over the data, the amount of reuse I can get is limited to how much work I'm doing per element in my array or range or whatever. And so I'm showing a ranges transform here. If I'm just doing a plus and a times, that's not very much work. And so that means that the cost of my algorithm is limited by the bandwidth, how fast my memory is. And that's much less fast than how much fast my arithmetic is on my computer. Whereas there's a large class of multidimensional algorithms where there's both more potential reuse and more realizable reuse, even if I don't have that much work per element. So I'm showing a dense matrix multiply on the right, but there are other algorithms that have similar reuse properties. And now I'm going to talk about coupling. So I talked about disjointness, I talked about spatial and temporal locality. Those are mostly abstract, like you can write your algorithms to exploit them. You don't necessarily, sometimes it helps to use non-standard, very system-specific libraries or instructions, but you can write portable C++ that respects disjointness, spatial, and temporal locality. And that's the amazing thing about C++. You can actually express all those things in it. And you don't even necessarily need hardware-dependent constants there. But there are some features of parallelism that are coupled to memory. And when I say coupled, what do I mean? So Some symptoms of coupling are restrictions on access. Like I have a thing, and it kind of feels like it should be an array, but it's not really because I can't get to the elements right. Overalignment is another symptom of coupling. So when I'm accessing memory, I'm only allowed to do it with a certain overalignment, or it's preferred that I do that and it'll be slow if I don't. There are also coupled sizes of memory accesses and parallel operations. And there are also local memories. Sometimes I get to see them and program to them, and sometimes they're under compiler control and I don't. And the effects of coupling are hardware-dependent choices. In particular, I would like those hardware-dependent choices to be things like integer constants, the sizes of things, the dimensions of things. But sometimes, unfortunately, I have to resort to variants of algorithms, like actual different algorithms. And an example of coupling I talked about before was bitwise operations on words. Those are parallel algorithms. Those are data parallel algorithms on your words. And talking about access restrictions, right? I can't get to a bit. I can't just change a bit. I can change the whole word. I can mask it out so it looks like I changed a bit. I can read a bit. I can write to the whole word in such a way that I'm writing to a bit, but I'm accessing the whole word. I can't just write to the bit. And I can't observe the storage order of bits. I know that there are bits and there's a conceptual or arithmetic storage order. I can pretend that there's a storage order, but I don't really know what it is. And when I do memory accesses on bits, those are aligned by characters. Those are aligned by groups of 8-bit. Actually, they're aligned by more than that, but the abstraction is character alignment, 8-bit alignment. And that's also coupled to the parallelism that's available in words. So I do my bit operations on words, not on bits. And words are kind of related to memory. I load and store words from memory, and I work on words, and I store them back. And I don't get to part of not being able to access the words is that there's a kind of a local memory, the registers in my computer. I load the words into those registers. I work on the registers, I put them back. Registers are a local memory, like we talked about with the Cray1. There's a register file. But I don't get to program to the register normally, unless I write assembly language outside of portable C++. The compiler deals with registers. I work with values. I program to values. And the compiler tries to put those in registers if it can. And there are also constants involved. So maybe on your computer, 32-bit words are faster, and so I should use 32-bit words when I do parallel bitwise operations. Maybe on your computer, it's 64-bit words. And those are constants. I have to know the hardware. Maybe if I'm writing totally portable code, I'm going to make that a template parameter or some parameter, compile time parameter of my function, and I may want to auto-tune or test it out or have different variants available. And in some cases, if you're really, I'm not a super bitwise parallel nerd. I don't normally do that every day, but there's some people who are really into using bitwise parallelism, and they know bits, they grok the bits, right? And they know that on some hardware you do it this way, and on other hardware you do it that way. And by do it this way, that way, I mean those are different algorithms, different parallel algorithms to achieve the same goal. Even though it looks like plus and times and or, those are different algorithms. And so those are algorithm variants that I may need to use differently on different hardware for better performance. I have another example of coupling, again, from the Cray1. So I talked about chaining. I talked about interleaving memory, interleaved memory with the IBM stretch. The Cray also had interleaved memory, and generally with a normal installation, you would have banks groups of 16. And when you're loading contiguously, you get one word per bank. And you can access the same bank once every 4 clock cycles. So if you load or store with a stride that's a multiple of 8, you would incur effectively a bandwidth penalty. So a latency penalty for each word, but for your whole array or vector, you would incur a bandwidth penalty. If you had a stride of 8, you'd have a bandwidth penalty of 50%, because instead of fully overlapping your bank latency, you incur a 2-cycle latency. And local memory has this thing called chaining that I talked about, where you can actually produce more than one instruction result per clock cycle by starting one instruction while you're in the middle of the previous instruction. And so by using this local memory, the register file for vectors, you could produce more than one result per clock cycle. But there was a coupling between memory and chaining, because if you had a stride that was a multiple of 8, you wouldn't be able to do chaining. On the Cray 1, you would miss the chain slot, and so you wouldn't be able to do this overlapping of instructions. And the trick was to pad your 2-dimensional arrays. So you would make the stride relatively prime with the number of banks. And that's a kind of an integer constant, right? There's a padding factor you have to know about for this hardware. And it turns out that this is actually useful for our GPUs as well, because our little shared memory units on the GPU, they have banks. And one of the tricks that people have done is to pad arrays to help avoid those bank conflicts. And I've also seen that on things like Sun Niagara, or architectures with a really low associativity of a cache, where sometimes you get a similar effect to bank conflicts where you're having a lot of cache misses. And so padding arrays can help with that too. That's a kind of coupling. Now returning to something that looks like element-wise data parallel operations, I'll talk about SIMD. And so with SIMD, you do get access restrictions. Your SIMD vec, your SIMD mask, that's not an array. You can't get a reference to an element. It's not a thing. You can't get a pointer to an element. There is a square bracket operator, and it looks like you're accessing an array, but it only looks like that. You get a value back, not a reference. There's no dot data. There's an iterator, but it's not a contiguous iterator. And there's an optimization reason for doing that, because as soon as I get a pointer to something in the middle of that SIMD thing, then that SIMD thing needs to live in memory, because I need to have an address that I can talk about. Like, I need to be able to write to it, read from it. And then it becomes an array in memory. And that we call materialization. Materialization means the compiler can't reason about this thing as a value anymore. It's required to make space in memory for it and put it there. And materialization means you can't just leave it in your SIMD registers. Now it's occupying memory, taking up space in your cache. Now you have to load it from memory into a vector register to operate on it, because a lot of times the SIMD instructions only work on things that live in the SIMD registers. The SIMD is local memory. Now there are size restrictions too. The standard has a minimum size, has a maximum size for SIMD. It's some implementation-specific, implementation-defined number. 64 is like the minimum of it. So I can't have SIMD of 1,000. Probably not. And I probably don't even want SIMD of 1,000, because it's not a power of 2, and a lot of SIMD instructions like powers of 2, and we'll optimize for those. And I talked about local memories too as another symptom of coupling. So users declare SIMD variables. That's how you use the std SIMD library. And the compiler will try its best to put them in SIMD registers. If I force materialization, then it can't, but suppose I don't do that. And the compiler then uses those SIMD registers as input and output to SIMD instructions. So there are little local memories. Just on the Cray 1 had a register file. Your computer with SIMD instructions has a register file for SIMD values too. And that's where the instructions have to use that local memory. SIMD operations also prefer or require over-aligned memory access, normally aligned to the SIMD width. They don't always require it on all architectures, but they will go faster, at least, if it's over-aligned. And that SIMD width is your integer constant to which you program. So I show an example on the right of a SIMD vec of float. So I have SIMD width of float things, and I declare over-alignment. I say, hey SIMD, this thing is over-aligned by SIMD width times a line of float. And then when I do partial load, what that means is load from this address, and I promise that address is over-aligned. And there's a little idiom there with something called iota, that Greek letter. And what iota is 0, 1, 2, and so on. And for SIMD iota, that's up to the vector size. So it's 1, 2, 3, 0, 1, 2, 3, etc., up to vector size -1. Thank you. And that's a common SIMD pattern for masking out-of-bounds elements. So we don't actually have that in C++26, but you can implement it yourself with the generator constructor. SIMD is really a system for creating locality opportunities. So you have hogs, and you can increase their spatial locality by turning them into spam. Sorry, I thought it was fun. You don't have to. So I talked about this pattern of I go over my whole global data structure, I load in little chunks, I work on them, squeeze that locality out of them, and then put them back. And so SIMD comes with those sorts of things. For example, SIMD comes with gathers and scatters. Gathers take my non-contiguous data that's all over memory and pull it in and make a contiguous chunk out of it. And that's an important enough operation that some computers have hardware acceleration for it. And I talked also about masked loads and stores. And what those do is I only load some of the elements, the ones where the mask is true. And where the mask is false, I just fill those in with a default constructed thing, like 0 in this case. And so gathers and scatters are about non-contiguous in memory. Masking is about non-contiguous control flow. So if statements that make data access non-contiguous. So it's a little bit like the copy-if algorithm, where the input might not be contiguous because of the if statements, the conditions, but the output is packed into something contiguous. And so this is really just getting to that I'm globally looping in parallel over all these little SIMD chunks, and then I work in a locally data parallel fashion over those chunks. And if I want to do that right now, I have two options. I could roll my own, or I could use the SIMD algorithms proposal, which I'll talk about in a bit. But if I have to roll my own global algorithms, first I have to assert overalignment. So I can use the various ways to assert overalignment, assume aligned, and the SIMD flags for overalignment. And then I have to do a parallel algorithm over an index range. So in this case, I'm striding across SIMD with groups of indices. And then my range is an index range, so I have to do index arithmetic. I have to create a mask to make sure I'm in bounds, and I have to do my loads and stores and vector stuff. So Matthias Kretz has proposed an integration of SIMD with the parallel algorithms. And that works by overloading on the execution policy. So changing the execution policy to the SIMD execution policy changes the behavior of the algorithm. It changes the element type of the algorithm, so it looks like a stood SIMD vec. And that's great because it handles all of the things that my previous example showed that you have to do, right? It handles the overalignment and ensures access disjointness and deals with all the loop indexing. But if you want to use the SIMD algorithms, you have to find your algorithm that fits the pattern of one of those algorithms. And furthermore, a lot of the range adapters in the standard are not contiguous range. And so you might start with vector or an array or something that's contiguous in memory, and as soon as I start applying range adapters to it, I lose contiguous range, and then I can't do SIMD loads and stores on that thing. So there's some open questions with this proposal. It needs an update for the parallel ranges algorithms, and it only talks about sequential SIMD iteration. So there's a design that needs to be done for how do I integrate. Oh, hi, Ruslan. Are you raising your hand?
If I may quickly comment,
Yeah.
I'm thinking in my head whether coupling parallel algorithms, including parallel range algorithms, and make SIMD as the policy is the good idea. Maybe it should be a set of separate algorithms. But that's like, it's an old paper. It needs to be revised, for sure.
Yeah, and it's not clear to me whether people want this.
They definitely want some subset.
Yeah.
Not necessarily all like 80 plus that we standardize.
Exactly, yeah. Yeah, and I'm sort of getting to that here, actually. So there's kind of there are different ways, there's a continuum of ways to express parallelism in your code. And there's a question like Ruslan brought up of where the SIMD algorithms belong in that. And so the continuum is about what I'm calling implicit versus explicit. So if I'm fully implicit in my algorithms, I just say, oh, I have an array, and I add it to another array. And that's parallel. Just parallel. And so fully implicit means that the system fully works out all the details of who maps the work items to the execution agents, and it says, I only declare interactions between work items locally. So I only, by adding two arrays together and saying that that's parallel, I'm just saying that element-wise, the corresponding elements line up. And I don't talk about global interactions between things. And with implicit parallelism, it's the system that ensures local disjointness, that I'm not writing to things concurrently in a bad way. But nevertheless, it's always the user who has to promise that my arrays are disjoint. And so there's really a continuum between array-based programming models. SIMD is an example of an array-based in that sense. It's kind of implicit how parallelism works. One could imagine Valeray. Valeray has had parallel implementations. People have talked about, I know Alfredo, who might be in the audience. Oh, hi. You talked about, you have a parallel array library, right?
Yeah.
Yeah, that's an example. Or there are other like programming languages where that's the normal way that you express parallelism. And the far explicit version of parallelism is I just manually create threads and I deal with the mapping of data to threads. But there's some things in between that are kind of fun. So the standard algorithms, the standard parallel algorithms, have element-wise parallelism. So I'm not working globally on the whole data structure, but I'm working element-wise, and I don't have to think about elements other than the current one. And I'm not allowed really to access them. And the Matthias's SIMD algorithms are an example of that. Partition-based parallelism, that's not something that we might be so familiar with in the standard. I'd show that example in Rust of split at and join, where I create the partition myself. So I declare, well, I want this chunk over there and that chunk over there, and it's up to me to decide how to partition it. So I'm kind of dealing with work items or dealing with load balancing myself. People who do distributed memory parallel computing normally think in terms of partitions. And so that's more natural for those people. Bulk chunked in std execution does create little partitions, or rather the system creates partitions and gives them to you. And when I say for each index, there's a kind of a level of indirection that's introduced. Instead of being parallel over your work items, like the standard algorithms, you're parallel over indices into those work items. And then you can decide how to map those indices to the work items, and you can access things that aren't the current element. So for example, if you want to do nearest neighbor computations, or you occasionally want to reach over there for some reason. And so it's up to you to be safe about how you do that. And like I said, the SIMD algorithms that Matthias had proposed are for each element style of algorithms. And that's not really very natural to people who do a lot of SIMD things for a living. Like people who do SIMD for a living, at the risk of overgeneralization, they don't trust the library. They barely trust. They want to touch the bits. They want to do it themselves. They want to write the indices, and now you're stopping them from doing that, and they're not sure if they get all the performance they want. And so, a lot of the advances that we made in the last two standards make it easier to do for each element kinds of parallel algorithms. So I think we shouldn't be afraid to try them. Even if we end up with a for each index design, we shouldn't be afraid to look at different ways of partitioning and expressing our parallelism. Now I'll have a bit of an interlude in multidimensionality. So one of the big motivations for having a way to express multidimensional algorithms and multidimensionality is that some multidimensional algorithms, a big class of multidimensional algorithms, have more potential and actual realizable reuse, temporal locality. And it's a little hard to see that if you just start with 1D algorithms. a lot of like the one-dimensional, the flat ranges algorithms, especially the ones that make one pass over the data. They access n elements, read, write, and they do one bit of work per element. And so the amount of work is also order n. And the potential reuse is, well, how much work do I have, and how much stuff do I have to read and write? Because the best possible case is that I get perfect reuse, perfect temporal locality, and then the amount of reuse that I could possibly get, the upper bound is work divided by data. And for many of the standard algorithms, that's just one. It's n work, n data, one reuse. And an example of that will be a dot product for vectors, which for the standard algorithms would be binary transform reduce. So I iterate over two ranges, element by element. I multiply up their elements element-wise, and then I add up the result. We can contrast this with adding more dimensions. And so I have on the right matrix multiply. So that's, if you're familiar with how summations work, I'm summing up the I comma j element of A with the k comma j element of B. So A is two-dimensional, B is two-dimensional, but there are three dimensions here. But then the result is also two-dimensional. So one of the dimensions got summed up, got reduced. And so because there are three dimensions, each of them is n, I really have n cubed work to do. There are other ways of formulating matrix multiply, and they also have good locality properties. I won't talk about Strawson or Winograd or those other ones, but just restrict ourselves to the n cubed version of matrix multiply here. So there's n cubed work, but there's only n squared data, 3n squared data. And so my potential reuse, n cubed divided by n squared, is n, like a lot more than with dot product. And it grows with my data. So the bigger my problem is, the more reuse I can get. But not all multidimensional algorithms are like this. So in the middle, I show matrix vector multiply. And matrix vector multiply, like I tried to show with the diagrams, it's kind of like a special case of matrix multiply where one of the things is rank 1 instead of rank 2. And like with matrix vector multiply, I really just, even though I get some reuse in the input vector, like I can imagine it as like dot product of x with the first row of A, dot product of x with the second row of A. So I get reuse in x, but it's still only order 1 potential reuse. So I have n squared data, I do n squared work. And I talked about chaining on the Cray 1. So operations like matrix vector multiply, they were part of the, like, chaining was really good at exploiting, as doing well at those operations because there was temporal locality to exploit, just not algorithmic temporal locality. And there are a lot of algorithms, like you may think, oh, matrices, linear algebra, that's kind of special. Well, there are a lot of algorithms like that. And it turns out a lot of algorithms that look like 3 nested loops are like that. And even if I have more nested loops, like for example, tensor contractions, those are really just matrix multiply, or I do a bunch of matrix multiplies. I can like rearrange the indices and put them together, and they're really just matrix multiply. A lot of things are matrix multiply. And I talked about potential reuse, but actual reuse is limited by my local memory size. And so that's why you design algorithms to fill up your local memory, read in a chunk, do as much work with it as you can, and then put it back. You're limited by your fast memory, your local memory size, your cache, or whatever. So a lot of what we call 3 nested loops algorithms behave in this way. And there's a lower bound on how much locality you can get, and a lot of algorithms can actually attain this lower bound. And the way that you get it is by breaking up your problems into little tiles, little chunks. And so there's an article with a lot of the theoretical foundations and some geometric insight there. So now I'll talk about cplus's support for multidimensionality, what we have right now and what we would like to have. So I'll build this up by starting with the not multidimensional case. So I talked about before how C++ exposes 4 ways, exposes one-dimensional parallelism in 4 ways. There's asynchronous execution, there's parallel algorithms, there are data parallel types and operations, and there are arrays. I'll start with arrays. We have a lot of those already in the C++ standard. So we have multidimensional array views, MD-span in C++23. We have slicing in C++26, so we can express different ways of accessing the MD-span. We don't have multidimensional containers. Thank you. So we don't have containers yet, or ways to make allocations that are multidimensional. There is an MD array proposal. That's a good start, but I think it needs some work. I'll talk about that. I'll kind of put together asynchronous execution and the parallel algorithms. So I guess, yeah, you can sort a multidimensional array, and that can have a meaning. But it's really like a thing that you do on a flat data structure. And so it's not like we need to go to the standard and we need multidimensional sort, man. We've got to have it. No, we don't need that. So there's a lot of work we don't need to do, and that's good. But with multiple dimensions comes new kinds of algorithms. And in particular, you have choices about subsets of extent, subsets of the dimensions. So for example, I might have a matrix, and I want to do row sums or column sums. I don't want to sum up all the elements. I want to go from my rank 2 thing to a rank 1 thing, or rank 0 thing. Maybe I go from rank 3 to rank 2 or rank 1. And those I call rank reducing reductions. There are also tensor contractions or generalizations of matrix multiply. And those are like the multidimensional version of binary transform reduce. So they're rank reducing reductions are like unary transform reduce. Tensor contractions are like binary transform reduce. Then there are other weirder algorithms. There are scans over subsets of the extents. Maybe you mix scans and reductions and for each. Maybe you have multidimensional data that's not regular. Like it's not just, can't express it with MD-span. Maybe it's kind of jagged and segmented scans, those sorts of things. There's so much to do here. Don't try to attack everything at once. Like, don't come with the omnibus proposal. And then I talked about regular SIMD. What is multidimensional SIMD? What is even that? So with MD-span, that's multidimensional array views introduced in C++23, and it generalizes span. And it has 3 parts. There's a data handle, and that generalizes the idea of pointer, something that's not uniquely owned, generally non-owned, but it could be shared pointer. There's a layout mapping, and that maps your multidimensional index to a one-dimensional thing, offset. And then there's the accessor, and the accessor takes the data handle and the offset from the layout mapping, and it gives you back a reference to the element. So the thing I show in the square black box there on the right is what the array access operator looks like in MD-span. It literally is that. I get the accessor, I get the data handle, I evaluate the layout mapping on my multidimensional index. That gives me an offset that goes into the accessor's access member function, and out comes a reference. So I talked about disjointness and locality. MD-span's layouts express those. They express disjointness and spatial locality. And the layout and you can ask the layout mapping for those things. So the layout mapping comes with queries: is X or is always X? Is always X is a compile time question, and is X might be a runtime question. So you can ask if a layout is unique, and that means it's injective, it's one-to-one. So every index maps to a unique element. And that's just disjointness right there. You can ask if a layout mapping is exhaustive, and that means it's surjective, it's onto, it covers the whole one-dimensional range. But it doesn't have to be unique. The example on the right there of an exhaustive layout is unique, but it doesn't have to be. It could be repeats there. And you can ask if a layout mapping is strided, and that strided means it's a linear function of the indices. So the strided layouts, I can evaluate a strided layout by computing the dot product of the indices with the strides, which are integers. And so those map to the things that we talked about before, the parallelism properties of arrays. Disjointness and unique, those mean the same thing. Contiguous means unique plus exhaustive plus strided. All those together give me contiguous. there's a caveat there because contiguity in the C++ standard also implies that there's memory and a pointer. And with MD-span accessors, I don't have to have memory or a pointer. Maybe some of you saw the really lovely CPPCon talk where somebody used MD-span to express a robot reaching with a little arm and grabbing a beer bottle out of a little box. That there's no memory there. I guess there's memory, but there's a box with beer bottles in it. So there doesn't have to be memory. Contiguous implies memory, but so I'm using that term loosely here. And sometimes I want to ask if some of the dimensions, some of the extents are contiguous. That can be useful for implementing multidimensional array copy, for example. And you can ask that by knowing that there are specific layouts that have that property, or knowing that the layout is strided and one of the strides is 1. So layout mappings have queries. You can ask all of these questions. That's great. Well, accessors don't have these queries. I mean, not only do I not know if it's in memory, I don't know if different indices point to different elements with an accessor because nothing in the standard says that that has to be true. That would be weird. Like, I would say idiomatic MD-span accessors have the uniqueness property. They have disjointness because you can express non-uniqueness with the layout mapping. And the MD-span design very consciously decouples layout mapping accessor. That's very conscious, deliberate, based on their experience with previous designs. And so it would be weird to express non-uniqueness in the accessor, I think. You just don't have to do that, and it complicates it. But nothing says that that has to be the case. The standard doesn't mandate that you write idiomatic accessors. So maybe we should think about adding queries to accessors, or maybe we should think about just saying that accessors have unique elements. I kind of like that rather than having queries, because what do I do with a non-unique accessor? It's weird. Okay, so for one-dimensional things, I talked about slicing and partitioning. In 1D, I can't distinguish those two things even for one dimension. And without having restrict or analogous declarations, compilers have a hard time deducing the interleaved views or disjoint. I showed that example of the striding of the two interleaved arrays, and without the restrict keyword, compilers have a hard time with that. And it turns out that when you write multidimensional algorithms, it's more likely that you'll create these interleaved layouts. So a classic pattern for matrix factorizations, for example, is to factor in place by partitioning it into 2x2 block matrix. There's a lovely set of publications that do this with a very beautiful computer algebra system, the Flame project from the University of Texas at Austin. But generally, that's an idiomatic way to express optimal matrix factorizations. And when you do that, it doesn't matter what layout you pick. I show on the right a column major layout, so layout left, where consecutive indices in a column are contiguous in memory, but you would have the same problem with a row major layout too. You'd have to write a funny layout. You can write a layout to make them each partition contiguous in memory, but that's not really natural for users. So you have this interleaved layout problem here. And now I'm showing here an example of LU factorization with partial pivoting. It just shows that this partitioning is a natural way to express the kinds of algorithms that we want to express. And so here I'm showing this partitioning operation. And because I don't have a partition in C++, I have to use slices here, so I'm using sub-MD-span. But that's how you write matrix factorizations in C++ now. And I would like partition. I don't want to have these slices that are living at the same time as their parent. And I would like some way to express that those are disjoint. I'm not really sure what that is yet. But I think we need more understanding, too, of how important is this really? Like, do I want to add something new to the standard? If I add something new to the standard to express disjointness of these slices, it needs to understand MD-span and span. Like, I can't just have it deal with raw pointers because, as the example on the right shows, a pointer and a size, that's not enough to express the kind of disjointness that we want to express, especially for multidimensional algorithms. So any declaration syntax would need to understand MD-span. So I talked about MD array before. It's a lovely proposal because you can go from, well, I need to like declare a layout mapping so I know how much storage I need so that I can make an MD-span. And all of the examples show this, and it feels really silly, and why can't I just have a container that does that? And that proposal has kind of stalled a little bit. And one of the reasons it stalled is because what happens when I move from an MD array? Well, MD array is not a container like vector. It's a container adapter. And it wraps your contiguous container. And that could be something that dynamically allocates like vector, or that could be stood array. And so the move from behavior depends on whether it's like vector or like array, but it's worse than that because in the standard, contiguous containers don't have a specified move from behavior. So let's say I have an MD array and it has some static and some dynamic extents, or it has all static extents. That's like the worst case. And I move from it. I would like those extents to become 0, but they can't because they're compile time extents. Like I can't change the compile time extents to be 0. And so if I have an MD array with all static extents, it should act like stood array always. Like, you know, stood array's dimension doesn't change when I move from it. It just, you move from the elements. And so like that lack of specification of move from behavior makes it really hard to reason about MD array in generic code. And it's a common pattern to treat MD array a little bit like an allocator. So you create an MD array, and then you partition it and do stuff with it, and then you call functions on chunks of it, and then you move it to the next thing. So you move it on down the chain. And that way you only make one allocation, and you can reuse it in different ways. But if I don't know what the move from behavior is, I can't write that kind of code. Another issue with MD array is that it conflates small and large. So when I create a stood array, that's normally small. Like I can't, otherwise I'll run out of stack space. Like I have compile time constants there. And it's a local small data structure working on local small things. And large is more like stood vector. I need an allocator. It's dynamically allocated. I want move to move the storage and not copy. Constructing a vector and copying a vector into another vector, those are global, those are algorithms. Those are parallel algorithms because I have a lot of elements and I copy them over there. Like, I don't know how many. I may want to run that in parallel. And the current MD array design has a constructor that takes an MD span. And that hides a parallel algorithm because that could be huge. And that hides a parallel algorithm that isn't aware of where my data want to live in the end. So my MD array could use a custom allocator, and the memory could be allocated on the GPU. It could be allocated somewhere where I need to be able to copy the data there fast. And it's all hidden in there, and I can't get to it, and it's hard to reason about, hard to write this code. And maybe I'd even like to run that asynchronously, but containers are not asynchronous. Like, just, that's weird, right? Containers are very synchronous feeling things. You create one, and then you can immediately access the elements. What is an asynchronous container? We've deployed in our Rapids Raft library, for example, an MD array version that has asynchronous CUDA streams in it, and the copies are asynchronous, and they're synchronized along the CUDA streams. And that works, but it's very awkward to fit that into container behavior. But it's funny, like users want their thing that looks like stood vector. They want it. And even if it's wrong, they want it. And so there's a struggle there. We want to give them the thing that they want, but the thing that they want is wrong. But the customer's always right. What do you do? I don't know. So I would like MD array to be a container, not an adapter. I mean, part of the reason for it being a container adapter was expediency of wording, literally. But it turned out to make the wording harder, which was funny. I think it should be two things. There should be all static extents that behaves like stood array, And then there should be the dynamically allocated version that behaves like vector, but it is not, maybe not resizable, maybe resizable, I don't know. And I never want a dynamically allocated multidimensional array that acts like a container, ever. I do not want that thing. So I will not write that proposal. You may write that proposal if you want. But so I wouldn't object to that if someone wants that, but I want the thing to be static. Okay, let's see. Now I'm going to talk about multidimensional for each. We have a proposal, and it combines a lot of elements. Ruslan's work on the parallel ranges algorithms, David's work here on fixing the ranges so that they work with the parallel algorithms, thank you, and that you can decompose them into iterators and sentinels. Like, a lot of this stuff didn't work until recently, and the views indices proposal, that's really amazing, like fixes views iota so that if I put 0 as the lower bound, it doesn't make my range an int. So views indices, that's great. Yeah, you got to use that. So okay, I have multidimensional for each on the left, right? That's multidimensional for each. This is a 3-dimensional loop. And I don't want to type that thing on the left. I don't, because there's some French philosopher involved, but you don't spell his name right. And what the heck? What's this Cartesian thing, right? And you, as the user, you have to unpack this tuple of indices. And it's only row major order. Like, you can massage your Cartesian product to get column major or something else, but it's painful. And there are other problems, like ranges right now with transform view and things like that. Those are not trivially copyable in certain cases where even the lambda is trivially copyable. So for example, I have a lambda, I capture an int by value. That's trivially copyable, it's just not assignable. But I put it inside of views transform, and now it's not trivially copyable anymore. And that's no fun, because then I can't run it on accelerators, I can't memcopy it over there. And so there's a proposal that Ruslan is leading to fix that. And also I can't portably optimize by specialization. So ranges is not really meant to be customizable. And so if I have a Cartesian product view in hand, I can't get at its subviews. And so I can't write my own algorithm customizations on Cartesian product. One of the customizations I might like to write is, I notice that I have a Cartesian product of these index views, iota view. That's a multidimensional loop. Why can't I take it apart, get the loop bounds out, the index bounds, and rewrite that as just nested for loop with my OpenACC pragmas on top, or OpenMP pragmas, or compiler extensions, non-standard compiler extensions, where the compiler knows how to optimize this really well. And so I can get all of those ranges. If I could get inside of Cartesian product, I could write specializations that do that. But I can't, because I can't get inside of Cartesian product unless I have something non-standard. So let's suppose I'm a library, I'm implementing the standard library. I would like to write the specializations like that. But then I need non-portable little hooks inside of my Cartesian product. And then my standard library becomes very special to me. And then my compiler can only work with my standard library. And I have to re-implement the whole ranges library to do specializations like that. And that's no fun. I shouldn't have to do that. And these are a bunch of motivations for our multidimensional for each index proposal. And so instead of writing this long thing that's hard to optimize and hard to specialize, I write something short. And it takes a layout mapping, because that gives me a preferred iteration order hint. And I talked a little bit about loop tiling before. In directives based in compiler extensions like OpenACC or OpenMP, I can tell the compiler that I want to break up the loop into little chunks. That's one way to reorganize loops for temporal locality. That's less useful if you have multidimensional SIMD, and I'll talk about that in a bit. And to bring back this implicit versus explicit hierarchy. So for multidimensional for each, like, I could start with an array-based approach. But those array-based approaches, they do a lot better if I have programming language support. So I show in that purple box on the left, on the bottom, something from Z-level programming language. That was an earlier array-based parallel programming model. And it's really nice to say, well, I want the index range shifted over to the north. I can just say north. I think I have to create north, but I can do that. The @ symbol shifts the domain over. Really cool. If I have indices, like on the right, like in the multidimensional for each index proposal, then I could just say that by accessing the array directly. And maybe that makes it a little harder to optimize for a higher level library, but at least I can say what I want to say. And element-wise, for multidimensional algorithms can be kind of weird. Like, I tried to show in the orange box what element-wise version of this stencil operation would look like, but it's ugly. It's not really natural fit. So you either go array-based or you go index-based, and we've gone index-based. I could talk about multidimensional bulk algorithms. That's just the asynchronous version. You could have of the synchronous algorithms that we talked about. But really, there's not much more here. The original intent for bulk was multidimensional. So if you look at the earlier versions of the proposals, the shape thing is called shape because it was meant to be a shape and not an index, not a size. So it probably wouldn't be hard to bring that back. But I think maybe we should think about dealing with the 1D asynchronous algorithms first, and like Bryce's proposal talks about. So there are other parallel multidimensional algorithms. We talked about copy, fill for each index. You could imagine a few more. When you have multidimensional arrays, you have new kinds of algorithms because you have more extents and more ways to do parallelism. Those are global algorithms over arrays. Maybe you want to use an array library for that. It's not clear what the form should be for the standard, but there are lots of libraries. Connor Hoekster's Parrot is a good one. Alfredo's library is another good one. So there are a lot of choices here for array-based libraries. I'm not sure what belongs in the standard yet. I want to talk about multidimensional SIMD before we go. It's just like SIMD, except it's multidimensional. That sounds silly. And what do I mean by multidimensional? Well, I talked about multiple dimensions lead to new kinds of algorithms. There are rank-reducing reductions, and there are contractions, like matrix-matrix multiply. There are rows and column sums, reductions over those different extents that result in something with a lower rank. And there are ways to reshape data so that instead of a 4 by 2, it looks like a 1 by 8. Or I could take the transpose, flip it over. But because it's SIMD, there have to be restrictions on things. It's not an array library. It's a SIMD library. So maybe you want to limit what the dimensions could be. Maybe you want them to be powers of 2. Maybe you want loads or stores to be aligned. Maybe you want to support only certain kinds of element types or reduction operations. And you want the array layout to be opaque. You don't want to be able to get pointers inside. That's not cool. And we have something that just came out called Qtile, and that's a kind of a manifestation or a version of multidimensional SIMD. So Qtile is a family of array-based programming languages. And we released our Python version in December. There's Julia versions and Rust versions. There's one in BASIC that Bryce helped release that we did just for fun. But the point is, like, it's not so hard to write different language bindings for it. And the C++ version is coming very soon. And these are all based on a kind of a virtual machine, a virtual instruction set that's meant to be portable. And the idea is, if you like to program in APL and you want a Qtile version of APL, you could implement a compiler that goes from your APL to tile IR, and then you immediately get Qtile APL. And Qtile works a lot like CUDA does. Users write tile kernels in a subset of the host language. Those kernels run on the GPU. In terms of the global algorithm, you get explicit. You have to do the global parallelism explicitly. It's like bulk, but multidimensional. You run over a grid of blocks, and within each block, the code looks sequential, but it's using these implicitly parallel tiles. So there are things that look like MD-span that are the global input and output arrays. We didn't use MD-span because there are restrictions on these things. You can't just access the elements. You have to go through views to get to the elements. tile is what we call multidimensional SIMD-VAC. And you could create different kinds of tiles. You can reason about shapes. They're all compile time things. Views are declaring intent to do aligned, tiled, load and store things. You can do loads and stores without them. Actually, there are views anyway, but views help declare access intent, so it can help permit optimizations. And there will be other kinds of views, and they'll support other access patterns besides tiled loads and stores, like strided for stencil computations. BID is a multidimensional block index. There's a kind of an index range construct, and the point of that is to help us optimize the for loop, but that's not required. And there are matrix multiplies and other kinds of computations. So there are a lot of talks about qtile. C++ release is coming very soon. Bryce and Stephen Jones, their talks show examples of qtile C++. I might want to talk about why we call it tile, or what would you call multidimensional SIMD-VAC. Don't call it MD-VAC. Like MD-VAC. No, don't. And it's not atomic. Like the thing you're thinking about is it's not a general array, and it partitions something else. Cell maybe is okay, but it's not a spreadsheet. Like it doesn't have that programming model that a spreadsheet has. Tile is pretty good because it partitions and covers something. Brick is not bad. You build structures out of it. So think about that. You would maybe want global multidimensional SIMD algorithms. We can think about that. Masking is really important generally when iterating over multidimensional SIMD things, because you have a tail. With SIMD, your tail is a one-dimensional thing, and so it's never bigger than your SIMD size. But the more dimensions you have, the more tail you have. And that makes masking really important, not just for ease of writing the algorithm, but also actually for performance. And one of the last things I want to talk about is you have all these, you have this coupling, right? And SIMD is all about coupling hardware and memory operations and little data parallel things. And so there are lots of integer constants. Maybe there are algorithm variations. Maybe you need to make choices at runtime. And so you need to compile things at runtime. It would be really nice if you had just-in-time compilation. Hal Finkel had a proposal a while back to do just-in-time compilation in C++. I think maybe reflection changes the way that we think about the syntax of that. So think about different notations for that. Just to wrap up, there's some open questions I've left for you all. We talked about restrict and disjointness and multidimensional arrays. How much compiler support does multidimensional SIMD need? Our qtile is a compiler. It depends heavily on compiler support. Could it be a pure library feature? But at the same time, like my background is not compiler, so I'm afraid of writing a compiler. But maybe I don't have to be anymore. It's a lot easier to do that now, to write a compiler, than it was when I was growing up. I'm counting grad school as growing up. And so maybe we don't have to be scared of writing a compiler. JIT compilation, giant open question. So just to summarize, I showed all the current ways that the standard supports one-dimensional parallelism, and then that naturally maps over to multidimensional parallelism. And those ways enable different properties. Like parallelism isn't just about parallel, it's about being able to be parallel. And so that's why I talked about disjointness and locality and coupling. And so there are a lot of things for us to do for people who want to write proposals or revise proposals, and a lot of things to explore. But I want to make sure you don't lose sight of the big picture of multidimensionality. And so part of the point of me giving this talk was to help convey the big picture. I like this quote from Emily Dickinson on moving. If you've ever moved, you probably feel how she feels, where you're trying to keep track of all of your things. I took at a time a memorandum of my several senses, and also of my hat and my coat and my best shoes, but it was lost in the melee, and I'm out with lanterns looking for myself. So let's keep track of your hat and shoes. So thank you all. I don't want to stand in the way of your coffee. So sorry, I ran just a couple minutes late, but if you have any questions, I'll be happy to answer them. Ruslan is first.
Yeah, so this MD, like whatever, CMD multidimensional.
Yeah.
Is there any other hardware that it maps to except yours?
So part of my job maybe will be to think about that. And I think people, so for example, Clang has the matrix type extension. And so there's a framework that we could use in compilers to experiment with that. But people who do graphics programming, they normally work with 4x4 or 3x3 little matrices. And so I would imagine that they have hardware support, or that there are ways to map those operations to SIMD. Like the original motivation for SIMD was graphics, right? And graphics has matrices, so.
Yeah, but I mean, okay, GPUs, maybe not only your GPUs, but I don't think it immediately maps to CPUs.
Well, if your multidimensional SIMD has powers of 2, then you could break it up into little chunks of local one-dimensional SIMD operations.
Yeah, yes, but not the direct multidimensional register. That's what I mean.
But even our mapping is not direct necessarily.
Okay.
Because we have to manage our local memories.
Mm-hmm.
So yeah, it's a fun open question.
Yep. Okay.
Any more questions? We're all so ready for coffee. I don't blame you. Okay. Well, come and find me if you have more questions afterwards. Thank you.
Great job, Mark.
Thank you. Thank you.